Hi students, in the last video we have discussed about the how to find out the transfer function of an analog Butterworth filter. Now it is a continuation of that. Now here what we are going to do is, so here we have find out this transfer function for omega c equal to 1 radian per second, right? So the pole location of the Butterworth filter, that is the poles, we are finding for omega c equal to 1 radian per second. Therefore the poles location of the Butterworth filter for omega c equal to 1 radians per seconds are known as the normalized poles. We are finding for this 1 radians per second, so it is called the normalized poles. But here but the design may vary. The cutoff frequency may not be 1 radians per second, so it may vary. If you want to find for different that is ohm c dash with different cutoff frequency, now we will get the poles location at ohm c is equal to, that is sk is equal to ohm c into sk. So this is known as the unnormalized poles. Okay. So for cutoff frequency 1 radians is said to be the normalized poles. For other than 1 radians per second, we are going to design an pole. So that poles are said to be an unnormalized poles. Okay. Now see the magnitude function. This is obtained for designing the transfer function for cutoff frequency 1 radians per second. Now here what we are going to do is, we are going to find out for different radians. So what we are going to do is, just I am going to change the equation as 1 plus epsilon square. This is a parameter related to a ripple in passband. Okay, so this is the parameter related to ripple in passband. So here there will be a ripple because we are not going to decide an ideal characteristics. You will have a ripple when you deviate from the cutoff frequency. So here we are having 1 plus epsilon square ohm plus ohm p 2 power n in the whole power 1 by 2. Okay, so now what we are going to do is, normally in FIR filter they will give the order of the filter, right? So here what they will give is, they will give the ripples, that is they will give the attenuation value, how much it is getting attenuated, that is attenuation in pass band and attenuation in stop band they will give from, and they will give the frequency, operating frequency. So from that we are going to design the order of the filter. Okay, so here we need to derive the formula in this regard. So we are going to derive the cutoff frequency formula for this. Okay, so now consider this equation. Here take a magnitude of j omega j ohm the whole square divided by 1 plus epsilon square ohm by ohm p the whole power 2n. Okay, now here what we need to do is, I need to find out this n. So for that what I need to do is, I need to remove from the power. So here if I have anything in the power, so if I take log I can easily remove. So I am taking logarithm on both sides. Okay, I am taking logarithm on both sides. So this can be written as 10 log. Okay, 10 log on both sides. Now it become 20 log magnitude at h of j ohm. Here 10 log 1 numerator minus 10 log of 1 plus epsilon square ohm by ohm p the whole power 2n. So this is the thing we will get it. Okay, now here what is the condition we are going to do is, I am going to substitute ohm is equal to ohm p. This operating frequency is equal to the passband frequency. So in this case 10 log of h of j ohm, this is the attenuation in the passband, which is equal to minus 10 log of, log 1 is 0, so minus 10 log of 1 plus epsilon square. So here for ohm I am going to substitute ohm p, so it will cancel. So I will get 1 plus ohm square. So I will have minus alpha p is equal to minus 10 log of 1 plus epsilon square. So epsilon square in this case. So what you will do is, I need to find first epsilon from this. Why I need to find epsilon is, here in this equation if I need to find n, I need to know epsilon, and these are all the things you know given depending upon the given, depends upon the given specification. Okay, so here minus alpha p So here minus alpha p minus 10 log of 1 plus epsilon square. So here what I'm going to do is I'm going to take remove log. If I want to remove log, I have to take anti-log. So 10 power pi, that is here 10 power point pi alpha p is equal to 1 plus epsilon square. Okay, so from this epsilon square is equal to 1 minus, sorry, 10.1 alpha p minus 1. So epsilon is equal to 10 point alpha p minus 1 the whole power 1 by 2. So this is the minimum, that is the parameter related to the ripple parameter related related in the pass band. Okay, so next one what I am going to consider is I am going to consider omega is equal to omega s. So first we have to consider two cases. For this ohm I am going to consider pass band frequency. Next I am going to consider the stop band frequency. Okay, now here the minimum stop band attenuation I am going to find out. Similarly I am going to use the same concept, that is magnitude of h of j ohm the whole square is equal to 1 plus epsilon square ohm s by ohm p the whole power 2n. The same equation I am going to take it out. Okay, so now taking the natural logarithm 20 log of h of j ohm, which is equal to 10 log 1 minus 10 log of 1 plus epsilon square ohm s by ohm p the whole power 2n. Okay, now what we need to do is I am going to equate this to minus alpha s. What we did there, here we have equated this to minus alpha p, right? So this is equating this to minus alpha p. Similarly here we are going to equate to minus alpha s, so which is equal to minus 10 log of 1 plus epsilon square ohm s by ohm p the whole power 2n. Okay, now here what you will get is I need to find out n now, because I know the value of epsilon. After substituting the epsilon here I am going to find out 2n. Okay, now this can be written as 0.1 alpha s is equal to log of 1 plus epsilon square ohm s by ohm p the whole power 2n. Okay, so this can be, when you, if you want to remove log, then that is 10 power 0.1 alpha s, which is equal to 1 plus epsilon square ohm s by ohm p the whole power 2n. Okay, so if 10 power point alpha s minus 1 is equal to epsilon square ohm s by ohm p the whole power 2n. Okay, so this can be written as ohm s ohm p the whole power 2n, which is equal to 10.1 alpha s minus 1 divided by epsilon square. So here epsilon square you will get it. Okay, so this epsilon square is nothing but here this is epsilon, so what I will get is 10 power 0.1 alpha p minus 1. Okay, this is what your value for this. Now here this is 2 power n, so I need to find out n. Okay, so what I have to, if it is in the power, what we need to do, we need to take the logarithm. First find out ohm s by ohm p the whole power n, so which is equal to square, taking square root, so 10 power 0.1 alpha s minus 1, 10 power 0.1 alpha p minus 1. Okay, now I am going to take logarithm since n is in the power. Okay, since n is in the power, so here 10 log of ohm s by ohm p. So listen, here ohm s by ohm p the whole power n is equal to this. If we want to have this n, what I need to do is I am going to take log on both sides. So what I will get is, so n log of ohm s by ohm p, which is equal to log of square root of 10 power point alpha s by 10 power 0.1 alpha p minus 1. Okay, so here n is equal to log of root of 10 power 0.1 alpha s minus 1, 10 power 0.1 alpha p minus 1 divided by log of ohm s by ohm p. Okay, so here how we need to take is, if you are having some fractional, that is you are having in decimal terms, so what you need to take it, you need to take this n greater than or equal to. Suppose I am getting n is equal to 1.2, I am going to take the nearest integer. Okay, so here n is greater than or equal to log square root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 divided by log of ohm s by ohm p. Okay, so here how we are going to write this again is, with here this can be written as, we what we we know epsilon is equal to square root of 10 power 0.1 alpha p minus 1, right? Okay, so alpha p minus 1, so this is epsilon, this denominator value. So here this numerator value can be written as lambda, which is equal to 10 power 0.1 alpha s minus 1, which is a factor. This is the ripple in the stop band. So this is the ripple parameter related to ripple in the pass band. Okay, so divided by log of ohm s by ohm p. So this n greater than or equal to. So this is the formula to find out n from the given parameters. Okay, next thing is we need to derive the cutoff frequency, new cutoff frequency from the given specification. It is not 1 radians per second. This is the new cutoff frequency what we are going to design. So for that we are going to consider these two equations. So we have already seen these two equations. Now what we are going to do is, just I am going to compare this equation. So when I compare this equation, I can equate these two. So when I equate these two and take reciprocal, I will get 1 plus ohm by ohm c whole power 2n, and this denominator I can equate it. So in this one, when I compare it, this one and will get cancelled, and ohm also get cancelled. Okay, so first step I have cancelled one, next I have written these answers. So now I am going to cancel this ohm. So this ohm p here I am cross multiplying, ohm p by ohm c the whole power 2 is equal to epsilon squares. I am going to find out only this ohm c, so I am taking the reciprocal. So ohm c by ohm p the whole power 2n 1 by epsilon square. Okay, so here this ohm c by ohm p alone I need, so I am taking this square root as already it is square, so divided by 2n. Okay, epsilon square divided by 2n. So ohm c by ohm p, which is equal to 1 divided by what is epsilon square. This we know that epsilon square is equal to 10 power 0.1 alpha p minus 1. Okay, so here 10 power 0.1 alpha p minus 1 the whole power 1 by 2n. Okay, I am substituting for alpha epsilon square. So this is power 1 by 2n. So cutoff frequency ohm c is equal to ohm p by 10 power 0.1 alpha p minus 1 minus 1 the whole power 1 by 2n. So this is what your cutoff frequency. So cutoff frequency can be obtained using this formula. Now this is the design steps in order to design an analog Butterworth filter. They will give the specification. So from the specification we need to find the order of the filter n. Then we are need to round off it to the next nearest integer. Then we are going to find the transfer function h of s for ohm c is equal to 1 radians per second for the value of n. So we have already designed, right? We have designed this transfer function for omega ohm c is equal to 1 radians per second, that we need to use it here. Then we need to calculate the cutoff frequency, use this ohm c. So we have find out this ohm c is equal to ohm p by 10 power 0.1 alpha p minus 1 divided by whole power 2n, right? So using this formula you need to find out. Then finally what you need to do is, we have obtained the new cutoff frequency. Now we need to replace s by ohm c. Here we are having h of s, right? So in that wherever you are having s, that we need to replace s by ohm c. Okay, in the next video we will discuss about the how to design analog Butterworth low pass filter. Okay, so you need to keep it in mind that here we are going to design only a low pass filter, that is a prototype filter. the design is only for omega c is equal to, that is the transfer function is for omega c is equal to 1 radians per second. If we want to find for new cutoff frequency, we need to have such transformation. So this is the procedure. Okay, in the next video we will see some problems related to this. Thank you.